In one of the previous topics, we studied the case of the capacitor, and we saw that the capacitor consists of two conducting plates that are parallel to each other, and that the capacitor works by building up opposite charges on its parallel plates. So we have two conducting plates building up opposite charges on their parallel plates, and therefore we have a potential difference established between them. In addition, we saw that for a capacitor we have a uniform electric field between its plates, which is directed from the high voltage point or from the high voltage plate to the lower voltage plate. In addition, we saw that the amount of charges stored in that capacitor, it was directly proportional to the amount of voltage applied, which was given mathematically as Q equal to C times V, where C would be a positive proportionality constant, which we label it as the capacitance of that capacitor. Now, in today's topic, we are going to be examining other features of the capacitor, or simply we are going to examine the behavior of a capacitor in an RC circuit. So we are going to study two different processes. We are going to study the charging and the discharging process that a capacitor can undergo in an RC circuit. In addition, we are going to determine a certain parameter which is called the time constant tau. So what's the time constant? The time constant is defined as the time it takes the capacitor to charge up to a certain percentage of its maximum value or to discharge down to a certain percentage from its maximum value. In order to do that, we are going to consider the following RC circuit. So let's consider that we have over here a resistor which is connected in series with a capacitor, and then the combination of the resistor and the capacitor are connected to a battery. And then over here we are going to consider that we have an on-off switch. So we are going to place an on-off switch over here. So we have a resistor, we have a capacitor over here of a certain voltage VC, and over here we have a battery. And these entire components are connected in series. So we have the following RC circuit. Now, in order to study that circuit and in order to study later on the charging and discharging process, first off we are going to consider two different time zones. We are going to consider a certain time zone right after we close that switch, and the second time zone which is going to be at t equal to infinity, meaning after a long time has elapsed after closing that switch. So the first time zone is going to be considered at t equal to 0, which is going to be the moment right after closing the switch, and we are going to consider another time zone at t equal to infinity. So starting at t equal to 0, right after closing the switch, what's going to happen in that case? Right after closing the switch, now we have the maximum amount of current I flowing through that circuit, meaning the maximum possible amount of current flowing through that circuit, which is generated by the battery. In that case, the voltage across the resistor is going to be equal to the voltage of the battery right at t equal to 0, meaning that right after closing the switch, the capacitor, it didn't start yet storing charges on its plates, so the voltage across it is still 0. So at t equal to 0, the voltage or the amount of charges stored in that capacitor is equal to 0. Therefore, the potential difference between the plates of that capacitor is also equal to 0. Therefore, the voltage across the resistor is equal to the voltage of the battery, and we have the maximum amount of electrical current flowing through that circuit, which is given by Ohm's law as V0 over R. Now, in case we didn't have VR equal to V0 at t equal to 0, therefore KVL would be violated. Therefore, we don't have a conservation of energy within that loop. So right at t equal to 0, the capacitor did not yet start storing charges on its plates. So for that matter, V0 is equal to VR, and we have the maximum amount of current flowing through that circuit. Now, what would happen after a long time has elapsed, meaning a long time after closing that switch? In that case, the capacitor has already started storing charges on its plates. Therefore, that current which is flowing through that circuit is no longer Imax, but rather it is a time varying current in that case. Meaning that as the capacitor is storing charges that current flowing through that circuit is going to keep decaying until we reach a certain point where the voltage across the capacitor is now equaling the voltage of the battery. In that case, that current I flowing through that circuit is going to drop to zero, because we have a component which basically behaves like a battery, which has two different terminals. It has a positive and a negative terminal that are opposing the terminals of the battery, but moreover, the voltage across that component now is equaling the voltage of the battery. In that case, the current flowing through that circuit is going to drop to zero after t equal to infinity. So after t equal to infinity, after a long time has elapsed, now the capacitor is fully charged. So now we have Q max, which is stored in that capacitor, which is equal to C times V0. And moreover, we have the voltage across the capacitor equal to the voltage of the battery. Therefore, the voltage across the resistor is going to drop to zero, because we don't have any electrical current flowing through that circuit anymore. And also we have the current I equal to zero at t equal to infinity. So we have these two different time zones, one right after closing the switch, and another one after a long time has elapsed after closing that switch, for which we have the maximum amount of charge stored in that capacitor. Therefore, the voltage across the capacitor is equal to the voltage of the battery, and therefore we don't have any current flowing through that circuit anymore, and for that matter, the voltage across the resistor would drop to zero. Now let's consider that after t equal to infinity, we removed the battery and we kept the resistor only connected to that capacitor. So we know that the capacitor, it can behave like a battery. So it is fully charged. Over here we have positive plates, over here we have the negative plate, and over here we have the resistor R. In that case, when removing the battery and when connecting the capacitor solely to that resistor, now the capacitor is going to discharge into that resistor, meaning that now we have an electrical current that is going to be generated by that capacitor, and as we can see, it's in the opposite direction of the initial current that was generated by the battery, and the discharging process of the capacitor begins. And this is actually when we introduce the time constants, whether for the charging process or for the discharging process. So the time constant is going to be the time it takes the capacitor, let's say, to discharge down to a certain percentage from its maximum value, whereas over here the time constant is going to be the time it takes the capacitor to charge up to a certain percentage from its maximum value. So theoretically we can distinguish the following time constants for the charging and the discharging processes. So theoretically, one time constant, which we label it as 1 tau, it corresponds to a charge up to 63% of the maximum value, meaning that now the capacitor has charged up to 63% from its maximum possible value of V0. And a time constant of 5 times tau, it corresponds to a fully charged capacitor. So these two time zones, or these two time constants, they correspond to a charging process of the capacitor. Now we can consider another two different time constants, but this time they are for the discharging process. So in that case, 1 tau would correspond to a discharge down to 37% of the maximum value, and then we have 5 tau, which is going to correspond to a fully discharged capacitor. So these two time constants in that case, they correspond to a discharging process for the capacitor. But what is actually impacting that time constant tau in the case? That time constant tau is being impacted by the parameters that make up that RC circuit. So these parameters are what? They are the resistance of that resistor and the capacitance of that capacitor. So theoretically, if you want to find the time constant tau, theoretically, it's given as the resistance of that resistor R times the capacitance of that capacitor. So tau is equal to RC, and the dimension of tau in that case would be seconds. And we can prove that dimension immediately by doing some replacements. So R, it is actually given by Ohm's law as, and C is given over here as Q over V. So we have V over I multiplied by Q over V. V and V they cancel. So we have Q over I. And then I, it can be expressed in terms of charge over time. So the current I is basically defined as the amount of charges flowing through a certain cross-sectional area per unit time. So that equation can be written as Q over T. So I is equal to Q over T. So Q and Q they cancel, and finally we are left with R times C equal to time. So over here, the time constant, it has a dimension of time, which is seconds. So that's how we can determine the time constant theoretically, by finding a value for the resistance and a value for the capacitance, and having therefore a reference value for tau over here, which we can compare it later on to our experimental values. Now, in order to determine the time constant tau experimentally, first off, we should know how the voltage is varying across that capacitor with respect to time, how the voltage is varying across the resistor with respect to time, and how that electrical current flowing through that circuit is varying also as a function of time. So we need to establish, first of all, equations for the voltage across the capacitor, for the voltage across the resistor, and for the electrical current flowing through that circuit, in addition to establishing an equation for the amount of charges stored in that capacitor. So once we establish these equations, we would be able actually to determine the time constant tau for any parameter. So let's say that we want to determine the time constant that correspond to a certain voltage across the resistor of 5 volts. So in that case, by having the mathematical equation for the voltage across the resistor, you would be able to determine the corresponding time constant for, let's say, the discharging process across the resistor. Or let's say we want to determine the time constant that corresponds to a certain value of the voltage of 15 volts across that capacitor. So by having a mathematical equation for the voltage across the capacitor, you would be able to determine the corresponding time that corresponds to that amount of 15 volts across the capacitor's plates. So how can we determine these expressions in that case? To determine them, we are going to be applying KVL, Kirchhoff voltage law, within that loop. So over here we are going to consider first off a certain arbitrary direction for that loop, a clockwise direction, and then we are going to add the polarities to each electrical component in that circuit. So over here we have a plus and negative for that resistor, and over here we have plus and negative for that capacitor. And then we start by applying KVL. So by applying KVL, we have what? We have over here V0, we are crossing from negative to positive, so we have plus V0 minus IR from positive to negative, so we have a voltage drop, minus IR, and over here we have minus VC. So we have V0 minus IR minus VC equal to 0. Now I in that case is what? We have defined previously I to be the amount of current flowing through a certain cross-sectional area per unit time. However, the current that is flowing through that RC circuit is a time varying current, but more specifically it is varying as we are storing charges on the plates of that capacitor. So in that case, that current I is going to be proportional to the rate of change of charges across that capacitor with respect to time. So whenever we are storing more charges in that capacitor, that current I keeps on varying. So basically I over here is equal to dq over dt, which is defined as the rate of change of charges across the capacitor with respect to time. So that equation over here becomes V0 minus dq over dt times R minus Vc. Now, with what can we replace Vc? Over here we have defined Q to be equal to C times V, therefore Vc is equal to Q over C. So we can replace Vc by Q over C. So minus Q over C equal to 0. And then we are going to do a separation of variables. So we are going to take all the dq variables to one side and all the dt variables to the other side. So that equation becomes minus dq over dt times R is equal to Q over C minus V0, so minus dq times R is equal to Q over C minus V0 times dt. So over here we have that Q variable, which is on the other side, we have to bring it to the same side of the dq variable, and then we take r to the other side. So we have minus dq over q over c minus v0 equal to dt over r. Now after reaching that equation, now we have to alter that expression in order to feature a term which corresponds to the time constant, because the time constant is going to be crucial in that case in any equation in order to determine later on the voltages or the currents or the amount of charges. So over here we have only the term r, and we need to multiply r by c in order to have a term for the time constant. So for that matter, we are going to take over here a common factor, 1 over c. So we have minus dq over 1 over c taken as a common term into q minus v0 times c, which is equal to dt over r. And then we can take c to the other side, and the equation becomes minus dq, or we can take the minus to the other side as well. So dq over q minus v0c equal to dt over rc, and the minus sign over here. So now we have done a separation of variables. We have all the q variables on one side, and we have the time variables on one side. So now what we need to do next is we need to integrate. So we are going to integrate that term and the other term, and over here we are integrating from 0 up to a certain arbitrary charge q, and over here from 0 up to a certain time t. So first off, we have the integral of dq over q minus v0c, which is similar to the integral of dx over x, which is equal to ln of x. So the first integral is going to yield ln of q minus v0c into, or from q from 0 to q equal to minus dt over rc, sorry, it's minus t, not minus dt, it's minus t over rc from 0 until t. So starting with that first term, so we have ln of q minus v0c. First off, we start by replacing q in that integral and that ln, so we have ln of q minus v0c, so it remains the same, minus, now we replace q with 0, so we have ln of 0 minus v0c. So that equation becomes ln of q minus v0c minus ln of negative v0c equal to minus t over rc. It remains the same, so minus t over rc. So over here we have ln of a minus ln of b. It can be written as ln of a over b. So we have here ln of q minus v0c over negative v0c, which is equal to negative t over rc. Now we need to get rid of the ln. To get rid of the ln, we need to take the exponential on both sides. So here we have the exponential of that ln, q minus v0c over negative v0c equal to the exponential of minus t over rc, which we can replace it with tau, or let's keep it rc. Let's keep it rc for now. So the first exponential is going to yield q minus v0c over negative v0c equal to exponential minus t over rc, and over here we have now q equal to v0c negative v0c times exponential minus t over rc. So now we have v0c as a common term, so q is equal to, or q of t, because now the charge is varying as a function of time, q of t equal to v0c into 1 minus exponential minus t over rc. However, v0c is none other but q max, which is the maximum amount of charges that can be stored in a capacitor. So therefore, q of t is equal to q max into 1 minus exponential minus t over rc. So that would be the first equation that we have established, which is going to be an equation for the variation of charges across the capacitor's plate. So that equation would be an equation for the variation of charges across the capacitor's plate. But that would be in the case of a charging process. So as we can see, it depends on Qmax and it depends on the time constant tau RC. Now from here we need to proceed in order to find an equation for the voltage across the capacitor, an equation for the electrical current, and an equation for the voltage across the resistor. So for the voltage across the capacitor, we know that Q is equal to C times V. So in that case, all we have to do is basically dividing that equation by the capacitance C in order to get the voltage. So the equation becomes, you have Q of T multiplied by the capacitance, divided by the capacitance is equal to Q max also divided by the capacitance into 1 minus exponential minus C over RC. So that first one over here, that first ratio would yield V of T, Vc of T equal to V0. So Q max over C is none other but V0 into 1 minus exponential minus C over RC. And that would be the equation for the voltage across the capacitor in the case of a charging process. Now, after establishing an equation for the voltage and an equation for the charge across the capacitor, we still need to determine an equation for the current in that circuit and an equation for the voltage across the resistor. So an equation for the current, it can be given as, we have defined previously that the current flowing through an RC circuit is a time varying current, which is given as dq over dt. And we already have an equation for Q, which is Q max into 1 minus exponential minus C over RC. So we derive that equation with respect to time in order to get an equation for the current. So I is equal to, so over here we are basically deriving that exponential which features time. So it becomes minus Q max times 1 over RC times exponential minus C over RC. So basically over here, T, it has the power 1, there is nothing left from it but rather only the term which is multiplied by T, which is 1 over RC, and then we multiply it by that exponential minus C over RC. But we have forgotten to add also a minus sign, which is the minus sign that is left from that derivation over here. So over here now we have a plus sign. So I becomes, Q max is none other but C times V0 times 1 over RC times exponential minus C over RC. So C and C they cancel, and then we have V0 over R, which is none other but I max. Therefore I of T is equal to I max into exponential minus C over RC. And that would be an equation for the variation of the electrical current in that RC circuit in the case of a charging process. And finally, in order to find an equation for the voltage across the resistor, therefore that equation over here, it can be actually multiplied by R. So we know by Ohm's law V equal to IR. So by multiplying each term by R, you would be transitioning from the current to the voltage. VR of T is equal to V0 into, or V0 times exponential minus C over RC. And that would be an equation for the variation of the voltage across the resistor. So as we can see over here, the variation for the voltage across the resistor is basically a decaying one. So whenever the capacitor is undergoing a charging process, the voltage across the resistor would be decaying. But moreover, if we have a look at the voltage across the resistor and the voltage across the capacitor, they both have an exponential response. Over here we have an exponential response for that voltage variation, and over here we have an exponential response for that voltage variation across the resistor. Meaning that graphically, if you want to represent the variation of the voltage across the resistor and the capacitor, you are going to represent it in terms of an exponential graph. So it's going to be either an exponential decay or an exponential increase. Let's consider that we have the following two graphs for which we are going to represent the variation of the voltage across the capacitor and across the resistor. So over here we have the voltage versus time, and the time is going to be none other but the time constant, the time it takes the voltage across the resistor to charge up or to discharge to a certain percentage, and the time it takes the voltage across the capacitor to charge up to a certain percentage. So over here we have 1 tau, 2 tau, 3 tau, 4 tau and 5 tau. Also over here we have 1 tau, 3 tau, 4 tau and 5 tau. So starting with the voltage, let's say across the resistor. So the voltage across the resistor, it starts at the maximum value the moment we close the switch. So for the resistor, we are basically starting at VR equal to V0. So initially the voltage across the resistor, it was equal to the voltage of the battery. So we are starting from the possible maximum value. And then we undergo a discharging process across the resistor. So over here we have an exponential decay that carries down until the voltage across the resistor drops to 0 after 5 tau. And over here after 1 tau we have a certain drop in voltage down to 37% of the maximum value of V0. Now regarding the capacitor, in the case of the capacitor, it's in the opposite manner of the resistor. We are starting at a value of 0 volts across the plates of the capacitor. So we are starting from the origin. And then the capacitor starts to store charges on its plates, and therefore the voltage on it is going to increment, but it's going to increment exponentially until the capacitor is fully charged after 5 tau. So over here we have the following exponential increment until we get to the maximum value over here across the capacitor, for which Vc is equal to V0 after a certain time constant of 5 tau. And over here after 1 tau we have a certain charge up of 63% of the maximum value of V0. So as we can see, the voltages across the resistor and the capacitor, they actually behave in an opposite manner to each other. Over here we have an exponential decay, over here we have an exponential increase. But in both cases we have an exponential response for the voltages. Now let's consider that the battery is actually supplying the RC circuit with a certain voltage of 20 volts. And we want to determine the voltage across the capacitor after a certain time constant of t equal to 2 tau. Like, what is the voltage across the capacitor going to be after a certain time constant t equal to 2 tau? In that case we have the following equation: Vc equal to V0 into 1 minus exponential minus t over Rc, and Rc in that case would be none other but tau. So we have Vc equal to 20 volts into 1 minus exponential. So now t, we replace it by 2 tau, so minus exponential minus 2 tau over Rc, which is none other but tau. So tau and tau they cancel, so we are left with Vc equal to 20 into 1 minus exponential minus 2. So by doing simple calculations, so you have 1 minus exponential minus 2 multiplied by 20, so that implies that the voltage across the capacitor is equal to 17.29 volts after 2 tau. In a similar manner, let's say now you want to find by how much the current in the circuit is going to decay after 2 tau. So we have I equal to I max into exponential minus t over tau, and I max is equal to V0 over R, and let's say R, it's around 50 ohms. Therefore, I would be equal to 20 over 50 times exponential minus 2 tau over tau. So you cancel over here tau and tau. You simplify your calculations in order to find a certain value for the current. And in a similar manner, you can carry on to find the amount of charges across the capacitor or the amount of the voltage across the resistor, of course by following the same methodology that we have followed over here, regardless of what time constant you are finding these parameters for. Now, so far we have studied the case of the charging process. We have determined equations for the voltage across the resistor and the capacitor, equation for the amount of charges across the capacitor, and an equation for the electrical current in that RC circuit whenever we had a charging process. Now, what if we have a discharging process? If we have a discharging process, first off we are going to be considering that circuit over here. So we have the resistor being connected solely to that capacitor. So all over again you are going to be applying Kirchhoff voltage law. So you are going to follow the same methodology that we have followed before in the case of the charging process. So over here you are going to choose a certain arbitrary loop, arbitrary direction for the loop, let's say a clockwise direction, and then over here you are going to assign polarities. So you have the current flowing in that way. So we have over here positive and a negative sign for the resistor, and then you start by applying KVL in that loop. So here you are crossing the resistor from negative to positive, meaning now we have a voltage lift. So it's going to be plus I times R, and over here we are crossing the capacitor from positive to negative, so we have a voltage drop, so it's minus Vc equal to 0. However, what is I in that case? We have defined previously I to be equal to dq over dt. But in that case, now the capacitor is losing charges. It's not gaining charges. So over here, that current I, we are going actually to associate it with a negative sign. So it's going to be I equal to minus dq over dt. So the minus sign is to indicate that now the capacitor is losing charges. It's undergoing a discharging process. Therefore, that equation becomes minus dq over dt times R minus Vc which is equal to Q over C equal to 0. And then from that equation over here you carry on in a similar manner to how we have done before. You are going to do separation of variables in order later on to establish an equation for the electrical current and that circuit, an equation for the amount of charges across that capacitor, and an equation for the voltage across that capacitor.